In this video, we're going to look at two different methods for adding vectors. We have this scenario: a plane is flying 350 miles per hour at 160 degrees. Winds are blowing 40 miles per hour at 60 degrees. And we need to find the resultant vector of the plane. Now, the first time I work this problem, I'm going to use the component form of the vectors. But before we get into that, let's draw a diagram of the situation described. The plane's flying 350 miles per hour at 160 degrees. So I'm going to make a little XY axis here, and my plane is flying at 160 degrees, and its magnitude, the magnitude of that vector, is 350. Now the winds are blowing at 40 miles per hour at 60 degrees. So at the end of this vector for the plane, I'm going to draw a vector that represents the wind. 60 degrees, 40 miles per hour. So if I add these two vectors together, the resultant flight of the plane would look like this. That's my resultant vector. And I'm going to work this problem using component forms. So let's start with the plane. My plane vector has a magnitude of, plane magnitude is 350, and direction is 160 degrees. So I have my formulas for converting magnitude and direction to component forms. The formula for x is r times cosine theta, and the formula for y is r times sine theta. So my x is going to be equal to 350 times cosine of 160 degrees. And if you put that in your calculator, the result is negative 328.892. Y is equal to 350 times sine of 160 degrees. And that equals 119.707. So now I have a component form for the plane. Negative 328.892 and 119.707. So now I need to find component form for the wind. The wind has magnitude of 40 and direction of 60 degrees. So to find its component form, I'm going to use the same formula as I used for the plane. X is equal to the magnitude of 40 times cosine of 60 degrees, and that equals 20. And the y component is equal to 40 times sine of 60 degrees, and that equals 34.641. So now I have the component form for the wind, 34.641. So now to find that resultant vector for the plane, I'm going to add these two together. So here's the two component forms, the plane component form in green and the wind component form in blue. If I add those together, then my resultant vector is negative 308.892 and 154.348. Now that's my resultant vector in component form, but what we really need to determine is the resultant magnitude and direction of the plane. So I need to take this component form and convert it back to magnitude and direction. So we have formulas for that as well. Remember, the magnitude squared is going to be equal to the x component squared plus the y component squared. It's just Pythagorean theorem. These x and y components form the legs of a right triangle with my resultant vector as the hypotenuse. So we're just using Pythagorean theorem. So the magnitude of my resultant vector squared is negative 308.892 squared plus 154.348 squared. And if you want to pause the video and put that in your calculator, if we put all that in the calculator and then square root the result, we get a resultant magnitude, of 345.308. Now, if your decimals are a little bit off from mine, I am copying and pasting these numbers in my calculator. I'm not rounding anything until I get to the end here, till I write this answer. So if you've rounded along the way, your answer may be a little bit different than mine. But that's our resultant velocity, 345.308 miles per hour. So the wind slowed the plane down a little bit. And we also need to find the resultant direction. So to do that, first of all, I'm going to find theta, and I'm going to call it theta ref for theta reference. This is our reference angle, because remember, when I put this into the calculator, it's going to give me an angle between negative 90 and 90. And then I've got to look at my vector and figure out what my angle actually is. So to find my reference angle, I'm going to do inverse tangent of the y component over the x component. So 154.348 divided by negative 308.892. And if you want to pause again and put that in your calculator, you can pause now. The calculator gives us negative 26.550. So if I go back and look up at my diagram, obviously my vector is going into quadrant 2, and so my angle should be somewhere between 90 and 180. But this 26 degrees that we got, that's actually representing this angle right here. That's our theta reference. That angle right there. And so to find my actual direction, what I need to do is add that negative 26 to 180. Whoops, sorry about that. So my actual direction is 180 plus negative 26, or just minus 26.550. And that resulting direction is 153.449 degrees. So that's how you add the vectors using component form. It's a little bit of work. Sorry, I just realized I wrote that answer over the watermark. Let's put that a little higher, 153.449 degrees. So it's a little bit of work, but it's a process that would be the same every time. You just find the component form of each of your two vectors, add the components together, and then convert back to magnitude and direction. Now I'm going to work this problem again using method 2. Our second method for adding vectors is using the law of cosines. Now we've got the same scenario here again. Our plane is flying at 350 miles per hour. Its direction is 160 degrees. The winds are still blowing at 40 miles per hour at 60 degrees, and I want to find the resultant vector. If I'm going to use law of cosines, the first thing that I need to do is figure out the measure of this angle right here between 40 and 350. That's the angle that I need in order to use law of cosines. Well, in my picture here, I know that this angle around to 350, that angle is 160 degrees, which means that this angle in here is 20 degrees, because those two angles would have to add up to 180. Now notice that the 350 degrees is that vector is a transversal between the x-axes of my two little x and y axes that I drew to start my vectors. This side right here, well, why is it not working? There we go. So there we have a transversal. And what that means is that if this angle right here is 20 degrees, then this angle in here is also 20 degrees. Now I also know that this wind vector is blowing at a direction of 60, and so those two angles together, the 60 and the 20, that together makes up the angle that I'm looking for. So that means that my angle here is 80. This angle, 80 degrees, 60 plus 20. So now that I have that information, I can do law of cosines. My resultant vector squared is going to be equal to 40 squared plus 350 squared minus 2 times 40 times 350 times cosine of 80 degrees, that angle that we just figured out. And if you want to pause right now and put that in your calculator, you can. If you put all of that in the calculator and square root your result, you should get, for the magnitude of our vector, 345.308 miles per hour, which is the exact same magnitude that we got using component form in the previous example. Now finally, we need to find the direction of our resultant vector. And in order to do that, I think I'm going to redraw the picture here. So I've got this side and this side. This is 40. This is 350. We figured out that this was 80. There's my resultant vector. And its direction is what I'm looking for. I need this direction right here. I know that this angle here is 20 degrees, and so if I could find this angle right here inside our triangle, then I could add those two together and subtract from 180, and that would give me my direction of the resultant vector. So let's find that angle. In order to do that, I'm going to use law of sines, because now that I have all of the sides, I can use law of sines. So sine of 80 degrees, and the side that goes with 80 degrees is our resultant vector, which we just figured out is 345.308. And that's going to be equal to sine of the angle that I'm looking for over 40, since 40 is the side across from that angle. So then sine theta is going to be equal to 40 times sine of 80 divided by 345.308. If I just multiply, I'm just multiplying 40 to the other side. Now remember, any time that we're looking for an angle, we have to use an inverse trig function. And so theta is going to be equal to the inverse sine of 40 times sine of 80 over 345.308. So pause the video again and put that into your calculator. When you do that, you get that theta is equal to 6.550. So 6.550, that is our theta angle inside the triangle. This angle right here. So if I add that to 20 degrees, then I get 26.55, but to find my direction, I need to subtract that from 180. So really what I'm doing here to find the direction is I'm doing 180 minus 6.550 minus 20. And that gives me a direction of 153.449, which is exactly the same direction we got working the problem using component form. Now again, if your decimals are a little bit off from mine, remember I am copying and pasting all of my numbers. I'm not rounding anything until my final answer. So if you round it along the way, you may have different answers than I do.